In this final segment, we're going to take a closer look at the concept of keys from a theoretical perspective. No particular diagrams to be had here, so we'll just operate off of the transcript. A key in theoretical terms is a subset of attributes on which all other attributes are functionally dependent. It's an important vocabulary term. This means that if you know the values for the key attributes, you can automatically determine the other attributes. If you know the ID of a person in the bakery database, that uniquely identifies the person, and all other attributes follow from it, for instance. Also, this must be true for any possible tuples in the relation, not just the particular ones in the relation at present. A customer table might have rows, none of which have the same last name. But that wouldn't be true for any possible customer table data, so last name isn't a key. And as condition 3 from our discussion of keys way back in the relational data model intro said, a key must also be minimal. It must not be possible to pare away one or more attributes and still have a key. A relation may have multiple keys. Any subset of attributes meeting the above criteria qualifies. If a set of attributes is minimal, and if other attributes are functionally dependent upon it, then it's a key. So, for instance, question 1 here. Identify two keys in a relation of courses that has the following attributes here. Two different sets will answer to those criteria, minimal and others are functionally dependent on it. Which two? Well, the course ID, as by way of answer, is certainly one key. And then also, if you look at it, the department and number combination would be a reasonable choice, since we would not expect one department to offer two courses with the same number. But I'll give you a bit of extra credit if you rolled your eyes just now and muttered, yeah, until some department recycles their course numbers a decade from now, reusing old ones for new courses. Recall our earlier discussions on the limits of humanly generated keys. Now, importantly, note that the minimality requirement does not invalidate department combined with number as a key, even though it has two attributes, while the key course ID has just one. Minimal means that no attribute in the key is superfluous, that the key is as trimmed down as possible. Any set of attributes, even a large set, can qualify as a key as long as none of its members are unneeded. Now, while we're being theoretically complete, a couple of terms you should also know: superkey and candidate key. There's a special term for a set of attributes that uniquely identifies a tuple, but is not necessarily minimal. If you remove the minimality requirement, then you get a superkey, a set of attributes that includes a key as a subset. A superkey is still unique across all rows, since there's a key inside of it. Superkey sounds like a more powerful version of key, but it's actually shorthand for superset of a key. And it is superset, by the way, not strict superset. So every key is technically also a superkey, since it includes itself. And some people refer to keys in general as candidate keys, with the implication that one candidate key will be chosen as the primary key. You should know this term as a synonym for key. Key, candidate key, same thing. But we won't use it in this course because candidate key sounds like not quite a key, which is misleading. Okay, let's wrap up with a few thought questions on keys and relations, just to make sure these ideas are clear. For instance, one interesting property of a key is that a projection to the key attributes always has the same number of tuples as the original relation. So, wait a second here. Projection is just a column choosing operation. Don't all projections then have the same number of tuples or rows as the original relation, simply cutting out some of the attributes? No, that's not true according to relational algebra theory. Why? Review carefully the definition of a relation and the fact that the result of a projection is a relation. The answer here is, at the risk of sounding like a parrot, a relation is a set. By mathematical definition, it has no duplicate tuples. A projection to a subset of attributes that are not a key might result in some duplicates, which would be implicitly eliminated. reducing the number of tuples in the projection. So for instance, if I do a projection to number and units on the course relation, that might produce duplicate tuples if two courses have the same course number and unit count. And the duplicates, per RA rules, are dropped, and the result has fewer tuples than the course relation. In looking at it from a SQL standpoint, a SQL statement standpoint might be a little clearer. Remember that it's a selected distinct number of units from course that is the equivalent of the RA projection, and that distinct would mean that we might have fewer rows than course itself as a result of that select. If there are no duplicates, because the subset of attributes is a key, then the projection has the same number of tuples as the original relation. So then in question 3, does that then mean that any projection that has the same number of tuples as the original relationship is projecting to a key? No, not that either. Having the same number of tuples is a necessary but not sufficient condition for a projection being a key. Why? And consider both uniqueness and minimality. Come up with a projection that has the same number of tuples, always guaranteed, as the original relation, but is not a key. And the answer is any superkey will also have the same number of tuples as the original relation. The key within it prevents any duplicates in the projection. Indeed, a projection that has the same number of rows as the original relationship, always has, can be used as the definition of a superkey. And then question 4, just once more for a review. Why is the SQL output of select first name, last name from customer not technically a projection on customer? Add the one extra word to that select statement that would make it produce a theoretically correct projection. And this answer should be pretty obvious from the above discussion. Select distinct first name, last name from customer. Theoretical projection results in a relationship with no duplicate tuples. And then one final interesting, kind of curious point. In theory, it can be shown that every relation has at least one key. And question 5, how can that be? What if the relation has a lot of duplicate values in its attributes? Might that not preclude finding any key? Remember that we may choose as many attributes as we like to form a key. That's important. The answer to this kind of, again, mostly just curiosity point is that if no proper subset of the attributes will work as a key, we can always choose every attribute in the relation as the key. If we do a select on all the attributes, even if it's a distinct, you'll still wind up with the same number as you started with. Now, that sounds like cheating, but the set of all attributes is technically a subset of itself. So by definition, the relation will have no duplicate tuples if it's projected to the full set of its attributes, and thus the set of all its attributes forms a key. This is of theoretical interest only, since the real point of a key is to be able to identify tuples using less information than is in the entire tuple, but it does drive home the theoretical definition of key and relation. So once again here, that's got to be a bit of a dizzying set of concepts. Let's do this in review. The distinction between superkey, key, candidate key, and primary key can be a bit confusing, so here's the brief summary from the top. Superkey. Any set of attributes on which the others are functionally dependent is a superkey. Equivalently, if a projection on a set of attributes always results, we should say, in the same number of tuples as the original relation, then the set is a superkey. A superkey uniquely identifies each row. It may also be a key, but this is not guaranteed because it might have superfluous attributes and thus not be minimal. An example superkey would be ID and last name in the customer table from Bakery 2. A row is uniquely identified by the combination of ID and last name, but it's also identified by ID alone. Last name is superfluous. But to be clear, a superkey doesn't have to have superfluous properties. The attribute ID alone is also technically a superkey and a key. Superkey means superset of a key, and the strict mathematical definition of superset of A is any set that includes all the elements of A and possibly includes even more elements. Thus, all keys are superkeys. They're supersets of themselves, but not all superkeys are keys. A key, or somewhat confusingly a candidate key, uniquely identifies a row, but unlike a mere superkey, a key is minimal. It has no superfluous attributes. All are needed to uniquely identify the row. And then primary key. The notion of a primary key is somewhat implementation specific, and it's not purely theoretical. The most important key in a table, the one most likely to be searched upon, and the target of any foreign keys from other tables, gets designated as the primary key and is implemented in especially efficient ways, for instance with a clustered index, as we've discussed earlier. But that is a practical distinction, not a theoretical one.